Thanks very much to particularly Henning and Tom and Andreas for organizing what looks like a really nice program. I'm sorry I couldn't be here all week, but unfortunately I was away. So I was just talking to Richard, actually, about what I'm going to talk about today. And I'm going to tell you about some of the approaches you should take in processing three-dimensional image data. And I was just talking to Richard. I was looking around for some of our data to show, and it was all over the place. So I'm going to end up showing quite a lot of figures from rather old but very important papers. And those papers that I'm going to refer to are summarized here. So these are really fantastic references that I would urge you all to have a look at if you really want to try and understand image processing in 3D. In particular, this one, very old and probably published well before many of you were born, I would imagine. But this ought to be compulsory reading for anybody that's doing 3D image processing. And it's one of those papers that you can just read over and over again, and you'll find new little interesting snippets of information. And then here are some later papers which basically describe the developments in processing for as you go to higher and higher resolutions. So the problem that we've got is that we're trying to measure structure factors in 3 dimensions. So you've probably seen this before, and the point that with these 2-dimensional crystals is that in the 3rd dimension you have a set of continuous lattice lines, and the problem is how do you extract structure factors from these lattice lines and then turn those into 3-dimensional structure. And it boils down to basically identifying the lattice lines, so giving them an H and K index, so identifying the crystallographic axes A star and B star, and then determining a height or a position in the 3rd dimension along the lattice lines. So the problem is really determining Z star. So we're trying to find out where exactly we are measuring when we tilt the crystal in the microscope. So to work out what Z star is, we need to know where the tilt axis is. So we need to know the azimuth of the tilt axis, and we need to know by how much we're tilting. So that's the basic problem, is determining the tilt axis and the position of the tilt axis and getting an accurate value of Z star. And then we have the problem of turning these measurements where we basically, taking a section through the 3-dimensional lattice and then turning those measurements into something useful that we can then use to do a Fourier synthesis to calculate a 3-dimensional structure. So I'm going to talk about 2 different cases, and I suspect that some of what I'm going to say will probably overlap with what Anqi Cheng is going to talk about later, but I hope that you'll find it useful if we're probably going to have slightly different perspectives on the way that you extract those structure factors. So I apologize if maybe some of it might turn out to be repetitive, but I hope it won't be. So this is a sort of very basic, simple scheme of steps involved in extracting those structure factors from tilted crystals. So we go through the normal image processing steps, which I'm presuming that you've already covered. So basically treat the image as an image of effectively an untilted crystal. Then we determine the contrast transfer function, but then we need to determine the tilt because we need to be able to work out what those Z star values are for each of the spots that we've measured. Once we know what the Z star values are, then we can merge all the data from different images together. And when we do that, we need to scale the amplitudes. So each image will have amplitudes on a different scale. We need to scale them all together. Once we've done that, then we can start to estimate the variation in amplitude and phase as we travel along these individual lattice lines. And this is a sort of cyclical process. So as you get better and better measurements of the amplitude and phase along those lattice lines, we can use those measurements to refine individual images against the data from all the other images, and we go through a cycle. And we have to refine the phase origin, and we can refine the CTFs, and we can refine the tilt angles, so we get better and better measurements of the Z star values. And one thing I'm going to try to emphasize is that you mustn't be afraid of manual intervention. Don't assume that everything will just be automated. Don't be afraid of intervening and looking at your data, and anything that looks suspicious, try and revisit it or get rid of the data or whatever you think is necessary to try and enhance the quality of your final calculation and finally determine the map. So at all stages, you want to be looking at your data critically. Don't assume that everything, by pressing go and just letting everything run automatically, that it's working properly. You need to be ultra critical all the time. So we've collected our data from our tilted crystal, and let's assume that we've been able to index it. So we can determine the crystal lattice parameters. So we've got H and K values for the spots. Now, in principle, that sounds straightforward. In practice, with highly tilted images, it can be rather difficult. So it may require a little bit of thought about getting the indexing right. But what we don't know is, for each spot, what its Z star value is. So we need to work out what that is. And to do that, we need to know how much we've tilted the crystal by and where the tilt axis is, where that axis is lying azimuthally. And there are different ways of doing this. One way, and particularly good choice if you've got very small tilt angles, is just to look at how the defocus varies. So let's say you've got a film, just look at the defocus in corners of the film, and that can give you an estimate of the tilt angle and the position of the tilt axis. And I believe there's even a program now, CTF Tilt, that will allow you to do that. For more highly tilted images, crystals, you can use a program called EM Tilt. And what that does, it basically looks at the crystal lattice that you've indexed and compares the dimensions of the A star and B star and the angle between them, which will be distorted compared to the lattice that you would get from an untilted crystal. And by comparing the distortions, you can work out the tilt axis and tilt angle. And that works particularly well for higher tilt angles. So you can get estimates of tilt axis and tilt angle, but again, be critical. If you get a number that is very, very different from what you were expecting, you ought to have, for example, some idea of what a tilt angle is because you've tilted the goniometer stage. So if you tilted it to 40 degrees and you get a tilt angle of 5 degrees or something, you need to wonder why that is. So be critical at all stages. Don't just assume that the program is going to give you the right answer. Make sure it makes sense. This is an area where you can get yourself into trouble if you're not careful. What's important is to know whether your Z star value is up or down. Do you have a negative or a positive Z star? So that really boils down to a question of which way you have tilted the crystal. And if you give it the wrong sign, the tilt, you'll end up with the wrong hand of your structure. So good to be slightly paranoid about this, because there are even instances in the literature where the hand has been misassigned. So a structure has been published as left-handed when it should have been right-handed. So you cannot be too compulsive about making sure that you've got the hand right. You'll find in the programs that there are various parameters that you have to enter, and this just shows a couple of them. So this parameter here is basically the angle from the tilt axis to A star, and then this is the angle here between A star and B star. These are two parameters that you'll see in the programs. Now, when it comes to checking the hand, one thing you could do is just think about your experiment. And let's say here's the tilt axis. And if we just look at the defocus and we find that, let's say, it's more underfocused on this side of the image compared to this side of the image. If it's more underfocused, it means that the crystal is lower in the microscope. So here's the crystal, A star and B star. If you think about it tilting in the microscope, so it's lower in the microscope, it means that you're cutting a section through here at a positive Z star. So just a quick check. Go and look at a particular spot. So let's say in the output of MM box, just look at a spot which you know is on a certain side of the image, and you know should have either a positive or a negative Z star. If you know what the Z star should be, just go and check that it has got the right sign of Z star. And if it hasn't, you've got the sign of your tilt axis wrong. So this is always something that you should do. Even if you think you know what the tilt angle is, just check that you've got the signs of your Z star values correct. Okay, so let's assume now that we've got estimates of our tilt axis tilt angle. So we've got Z star values, we've indexed the spots, we've got HK values, we've got HK Z star values, and we've got amplitudes and phases now from a whole bunch of different images, and we need to bring those all together. So we've got to refine them all to a common phase origin. And in the MRC software, the program that does that is ORIG-Tilt. And we've corrected the amplitudes for the contrast transfer function. And what we need to do is bring together measurements of amplitude and phase, which are nominally measurements from the same HK and Z star value. Now, in practice, in principle, that would not be possible because you've got a whole bunch of random sections across the 3D transform, all with different Z star values. But what you can do is assume that within a certain Z star limit, all measurements should be the same. So what we're going to do is bring together measurements that are locally within a certain value of Z star for each of the diffraction spots. So let's take a slice, a two-dimensional slice through this 3D view. So here's the A star, B star plane. Here's Z star. So imagine we have a slightly tilted image here. So here's the untilted image. Here's a tilted image. And the vertical blue lines represent those lattice lines. And we have zones of Z star, for instance, approximately 1/3 of the reciprocal thickness. So let's take zones that are about 1/3 of the reciprocal thickness and assume that any Z star values within those zones are identical. So that means that all the phases can be compared between the untilted and this tilted crystal within this zone here. So we can compare all these phases and try to merge them to the same phase origin. Obviously, with highly tilted images, you can do fewer comparisons. So in this case, we've only got one spot for this highly tilted image, which we compare against the other images in our merged set. So what you want to do is basically slowly step out towards increasing tilt angles, merging and refining the images, going to higher and higher tilt angles as you start to bring them all together, and just doing comparisons within these narrow Z-star limits. And by doing this, by trying to merge and refine all the data to its common phase origin, by looking for the best agreement, generally you end up with a Z origin at the center of mass. So it just kind of happens automatically. But you've got to be careful here. So again, don't just do this blindly, automatically, thinking that if you feed all your images into Orid Tilt, press go, it'll all work, and the answer you get out at the end is correct. Look at it critically. So for example, if you look in Orid Tilt, it produces a matrix like this, which is basically a scoring matrix. So here are, this would be, for example, the phase shifts along X and along Y, and you get a scoring matrix based on the phase residual at different phase shifts in X and Y. If you get a nice peak like this with a high score, this is a very clear and unambiguous score and a quite clear phase origin for the film that's being compared against the others. But often with tilted data, you may have very, very weak, poorly measured phases, particularly perpendicular to the tilt axis. And so you can end up with rather ambiguous phase origins. So for example, here, we've got one that it is really not clear. You're getting similar kind of scores spread over quite a large array of different phase shifts, and it's not clear whether the peak should be in here or it's here, and sometimes you can get them streaked out. It's very ambiguous. The program's always going to try and find the minimum. By definition, that's what it's being told to do, but it doesn't mean that it's giving you the correct value. So be critical. If you start to see this situation where you've got a very ambiguous phase origin match, be critical. Look at your data. Maybe your data aren't good enough. Throw them out. Move on to the next image.
Just to have round on the... So this is pixel by pixel, and if your pixel is...
No. So what we've got here is... so you're applying a phase shift to so many degrees. So let's...
Corresponding to which distance, if you wish, when you shift?
Let's say... Well, let's imagine we were doing, let's say, a coarse search of, let's say, 6 degrees or something, step size. So you're stepping 6-degree phase shift on the 0, 1 and the 1, 0 of one film compared to the others.
Okay.
And then you're looking at the phase residual for each of those phase shifts. And here we've got an excellent score. So that's telling us that the phase shift, so if this was 6-degree steps, so here we'd be doing a phase shift of 18 degrees in this direction and 24 degrees in this direction. Whereas here, not quite clear what phase shift we should be applying to the image.
nevertheless, this all translates into distances.
Yes, yes. So 360-degree phase shift would be 1 unit cell. Yeah.
Sure.
Now, I'm only talking about images, and not always do we have the luxury of having well-measured electron diffraction amplitudes, so we're going to have to get amplitudes from the images. And those amplitudes are typically rather badly measured for various reasons. First of all, you've got the fall-off of the envelope of the contrast transfer function due to limited coherence, for example. You could have poorly ordered crystal. You could have sample movement in different directions, blurring your image. As you tilt your crystals, lack of flatness becomes more of a problem, and that manifests itself as blurring of spots. So you can end up with rather poorly measured amplitudes, weak amplitudes, and those amplitudes, the way those amplitudes fall off may be different in different directions. And if you want to calculate a structure, you want to have a better estimate of those amplitudes. And if you don't have electron diffraction amplitudes, you're going to have to use the image amplitudes. So you can attempt to correct them. So first of all, we need to correct for the contrast transfer function. So if you know what the contrast transfer function is, that's relatively straightforward, just adding a scale factor depending on where you are along the contrast transfer function as it oscillates up and down. But then we have other factors that we can also correct for, and this is a scheme. So this is described in one of Richard's papers with Wendy Havelka, and I've given you the reference, that tries to allow for an anisotropic fall-off in amplitude for tilted images. And basically what you can do using this program, Scale IMAMP, is compare your observed amplitudes against a set of reference amplitudes. And this shows how they might fall off. So here would be your ideal ratio of reference amplitudes to observed amplitudes. But in practice, for different films, you get fall-off by different amounts. And those fall-offs are described by a temperature factor. So it has the same effect as the temperature factor that you would see in X-ray crystallography. It's not quite the same thing, but for convenience, you call it the temperature factor. And basically, it describes the slope of this fall-off. So here, this is resolution along here, and this is the ratio of image amplitude to diffraction amplitude. So what we want to do is try and beef up these amplitudes to make the ratio follow something like the ideal. And this means that you need to have a reference data set. And there are different choices for a reference data set, but let's imagine that you have a crystal that you know is a membrane protein full of alpha helices running more or less perpendicular to the membrane. It would be quite reasonable to use something like diffraction data from Bacteroidopsin, which is also made up of alpha helices running perpendicular to the membrane. And you can scale roughly against those reference data. And you might typically end up applying temperature factors, let's say, of something like -500 to bring these slopes up to the horizontal. So that would be, let's say, at 7 angstroms, I think that would be equivalent of increasing the amplitude by a factor of 12 or something. So you're basically sharpening up the high-resolution data. So it could be that you've actually got quite good phases at high resolution, but you're not seeing a high-resolution structure because you haven't corrected for the amplitude. So you sharpen up the structure by beefing up these amplitudes. Now, in practice, you can get very, very silly temperature factors, particularly if you have rather limited data perpendicular to the tilt axis. So in practice, you want to limit the temperature factors to somewhere between 0 and 1,000. Because otherwise, you can end up with silly temperature factors in some cases of 30,000 or something, which is just not realistic. So you've got to be somewhat pragmatic about the temperature factor that you assign. So let's then assume that we've got our measured phases, and we have our corrected amplitudes. Then we need to figure out where they are lying on along the lattice lines in the Z star. And here is an example of some data from our lab. I can't even remember what it is, but basically you end up with these, and I'm sure Angie Cheng will talk about this in more detail, but basically you end up with a plot of, this is, so we've got resolution here, and here we have amplitude, and here we have phase. And each of these crosses represents an individual measurement from a film. And we've merged them all together, we've refined them to the same phase origin, and you can see typically that the amplitudes can be rather widely scattered. And more typically, the phases tend to agree somewhat better. But the point is that these measurements are not at discrete points along the lattice line. So we're sampling the lattice line at all different points along Z star here. So we need to convert, before we can extract useful Fourier terms for making a Fourier synthesis, we need to turn this scattered data into a set of curves. And that's what lat line does. But you can, sometimes, you'd be better off just doing it by hand. If you've got, let's say, rather low resolution data with a lot of scatter, you might be better off doing it by hand, and you can just draw by hand through the data. If you use automated procedures, for instance, by trying to fit sync functions to the data, you can get into terrible trouble if your data are rather noisy. So you've got to be very, very careful. Things to look out for: are there any extreme outliers, particularly in the phase? So you get a lot of scatter in the amplitude, but if you get what you think is a well-measured spot that is well away from the curve, go back and look at that spot. Look at the film. Has something been done wrong with that? So again, do not be afraid of manually inspecting your data. Don't assume that the programs are just going to automatically do everything correctly for you. If you're hand drawing, you need to do some thinking sometimes. For instance, so you need to take into account how amplitude and phase are related in the complex plane. So here's an example. Phases can change much more rapidly along Z star when the amplitudes are small. So here we have two amplitudes, a big one and a small one. If we change it ever so slightly by the same amount, you see that the phase angle changes much more rapidly for this small amplitude. So if you're fitting by hand the amplitudes, and we've got rather low amplitudes here, you can expect quite reasonably that you get much more rapid changes in phase. So check that that makes sense, that that's all happening. The other thing is, if the phase changes by 180 degrees, the amplitude must go through 0. So you've got an amplitude of 1. If you're changing the phase by 180 degrees, you're swinging around to an amplitude of -1. To do that, you have to go through 0. And here's an example. So here we've got a phase roughly around 0 degrees for a while. And then all of a sudden, we get this rapid change in phase by 180 degrees. And if that happens, the amplitude must go through 0, which is exactly what's happening here. So if you're hand drawing, you need to think about these things. If you're using automated procedures, it should deal with this automatically. So I think maybe Anchi will talk about this in more detail, but the automated methods basically try to fit sync functions to automatically draw out lattice line curves. And this is based on the assumption that basically a 2D crystal is a 3D crystal that you've multiplied by a top hat or square function. So if you do that multiplication in reciprocal space, you've got a three-dimensional Fourier transform which is convoluted with the Fourier transform of this function, which is a sync function. And you basically, in a simple-minded way, the way you can think of it is that you're laying down little sync functions all along the different points of the crystal lattice to make up the final curve, adding them together. And the MSE program Latline will do that for you. But don't use it blindly. Just look at the curves. Do they make sense? You can add constraints in Latline. So you can, for instance, tell the program that outside certain limits there must be no density in the third dimension. So that provides a constraint on the way that you fit those data. So keep looking at your plots. Check them critically. Do they make sense? So here's some data that are scattered all over the place and it's rather noisy in places. So one thing that you might often find, particularly at higher Z-star values, you may have just one or two measurements, and those one or two measurements may be very, very weak, so sort of IQ 6 or 5 spots or something like that. So you can end up with unrealistically high amplitudes being fitted. So here we have amplitude, here we have phase for a particular lattice line. And out here, we've got rather unrealistically high estimates of what the amplitude is. In this case, we've also got very, very high error bars. So actually, those data would be weighted down when you come to calculating your map. But you'd be just as well probably to throw these data out. They don't really mean very much. So look at these and check that you're not getting these huge peaks shooting off to ridiculously high amplitudes. So they'll be rather meaningless. So we've made these curves of amplitude and phase along Z star, and then we want to turn those data into a structure. And to do that, we need to sample those curves discretely, as though we were actually measuring data from a three-dimensional crystal. So you can sort of think of there being a unit cell in the third dimension, and that we're going to sample the Fourier terms, the amplitudes here and phases here at discrete points along the curves. And you want to make sure that those sample points are fine enough that you can follow all the variations in amplitude and phase. So the thicker your sample, the more these curves are going to oscillate up and down. And you want to sample finely enough that you can adequately sample those variations in amplitude and phase. And once you've done that, then you end up with a list. You've got an H, a K. Now instead of a Z star value, which could be any value along a continuum, we've got discrete L values. So we've now got that third index for the third dimension. We've got an amplitude, a phase, and then some estimates of error in amplitude and in phase. And then we can calculate, just using standard X-ray crystallographic programs for three-dimensional crystals, we can calculate we can do a Fourier synthesis to calculate our structure. And typically, what we do is calculate that structure using Fourier coefficients that look like this. So we've got the amplitude, f, and the phase, phi, and we weight it by a figure of merit. And this is something that X-ray crystallographers are very familiar with. As microscopists, you might not be so familiar with it, but basically it weights the contribution of each of those Fourier terms depending on the phase error. And in X-ray crystallography, this produces what's called a least error map. So if you have a very, very high amplitude, but it has a very, very high phase error as well, you want to damp down that amplitude. You don't want that amplitude distorting your structure by making a really strong contribution when the phase error is very, very high. So you need to weight down using these figures of merit. Now, when you tilt, in principle, you've got a problem because you can't tilt to 90 degrees. So you're going to end up missing some data. And this may not be a great problem. If you have lots of well-measured data all the way out to 60 degrees, you're covering a lot of reciprocal space. In practice, you're not going to get those perfect data. And in particular, you're going to end up missing any data along 0, 0L. So you have no measurements along 0, 0L. And that may not be a problem. So if you have a bunch of vertical alpha helices which have very little contrast sort of across in the plane of membrane, that might not be a problem. But if you have some structure which has very contrasty features that run parallel to the plane of the membrane, that could give you problems. Because basically, if you set all the amplitudes along 0, 0L to 0, which is what you're doing if you're not including them in the synthesis, you're going to end up with a mean density of 0 on each section in Z as you calculate the structure. So it may not be a problem, but if you've got some feature, let's say some big density that's lying in the plane of the crystal, you could end up with a problem if you're setting each section to a mean density of 0. So it's just something to think about, but not necessarily worry too much about, but you can try and do something about it. And there are different ways of estimating the 0, 0L values. So you might have some powder diffraction data, or you can cut sections perpendicular to the crystal, which might give you some indication of how density is varying through Z. Or you might have side views where your crystal's folded over. Or you can just look at the contrast as it varies across the structure. So you might see different variations in contrast as you go along the thickness of the structure, which may give you an indication of how the density is varying. And you can try then from these data to try and get some sort of estimate of what the amplitudes and phases should be along 0, 0L. So I've talked about a case where you've got low resolution, relatively small image, where you process the data initially as though they were untilted. If you've got a very, very large crystal and you're talking about high resolution, you encounter a new problem that you've got to take care of. Here's an example. Let's say we're imaging a crystal that's a micron across, and we've tilted it by 30 degrees. You look at how the defocus changes by 5,000 angstroms from one end to the other. So you can't do a simple-minded CTF correction by applying one set of defocus parameters. In other words, you've got two values of defocus and then the astigmatism angle. So you cannot correct for defocus and astigmatism by assuming one set of values. If you've got a tilted large tilted image and you want to look at high resolution data. So for example, here's some data of ours on one of our crystals, and let's assume that we're down at this at one end of the structure of the crystal, and the defocus is relatively low. So all the spots within this zone have negative amplitude, and then we change to positive amplitude within this zone of the CTF, and we'll go negative, positive. So we've got oscillations in the CTF, which you're completely familiar with. But then go to the other end of the crystal. Because it's tilted, the defocus will be completely different, and it'll be much more highly defocused. And we end up with exactly the same crystal, but the spots are in completely different zones of the contrast transfer function. So now within our positive zone, we've got this ring of spots here, which at the other end of the crystal, we're in the negative zone of the CTF. And then we go to the next positive zone there, and those remain at the other end within the positive zone. But beyond that, we are in the negative zone, and yet here, they were still in the positive zone. So the spots will have reversals in contrast that are different at different ends of the crystal. So you can't assume a single defocus value. And so it goes on. So we have to deal with this problem. So here's our tilted crystal. So let's imagine that our crystal is made up of a repeating lattice, and let's just think of one component, one Fourier component from that lattice. So here's our repeating component in real space as we go across the crystal. And in Fourier space, that gives you two Friedel-related spots here. So we've got two values which represent, so the distance here represents the spacing of this Fourier component. Now, as we travel across the image and as the defocus changes and we go in and out, positive, negative, positive contrast, basically the contrast of that component is going to oscillate between positive and negative. So we're going to end up, so we start off, let's say, with a black feature on a white background. We oscillate through to a white feature on a black background, and then we get all sorts of intermediate stages, and at some points where you get no contrast at all. And then we oscillate back again. So the contrast keeps oscillating as we travel across the image, and the defocus changes as we go across. And the effect is basically, it can be described by this function here. This is a tilt transfer function. And it's basically describing how the contrast of a particular Fourier component is oscillating as we travel across the specimen. So we're going from positive to negative, back to positive, negative. So it's a sinusoidally varying oscillation between positive and negative contrast as you travel across the crystal. And a way to think about this is that we're taking our real space structure, so here's one component of the structure, and we're multiplying it by this tilt transfer function. And in reciprocal space, that's equivalent to doing a convolution between the Fourier terms for that component of the structure and the Fourier transform of this tilt transfer function. And the Fourier transform of the tilt transfer function is this sort of double peak. So we do a convolution of this double peak with the diffraction pattern of the crystal itself. So we end up at each peak position in the diffraction pattern, we end up with this double peak structure. So with the spot, think of this as a diffraction spot, it gets split. So instead of a single spot, we get a splitting of the spot. And the distance between those two peaks in the split spot is a function of the number of times you repeat this sinusoidal oscillation. So the more repeats you get within the image, the wider these spots are going to be. So that's going to be a function of the resolution and the tilt angle, and here's a summary of what we end up with. So we've got this tilt transfer function. The result is that we end up with a particular, so think of this as a particular diffraction spot. The spot gets split. So if it was untilted, the spot would be here. But in the tilted image crystal, the spot is split into two components like that, separated by an amount that depends on the number of oscillations you've got in the tilt transfer function. So we need to correct for this because we want to measure the amplitude and phase at the predicted spot position. And the way that's done is basically you multiply the image by the tilt transfer function. So you're basically squaring this. This is the correction that you end up applying. And when you do that, you recover that central peak, but you end up with two little satellite peaks, which are twice as far out as these two. And the reason they're twice as far out is if you think about it, we've got the number of oscillations is twice as many now. So we're twice as far out, and we're recovering that central peak. So now we can go and measure the amplitude and phase at that peak where it's been correctly restored. So in principle, what you're doing is you're multiplying the whole image by that tilt transfer function. So you've got to get an estimate of what the tilt transfer function is. In practice, the whole calculation is done in reciprocal space much more efficiently, and you do a convolution with in reciprocal space rather than a simple-minded multiplication in real space. So the tilt transfer function can be worked out, and here it is described. So if we have a point of interest, we can measure its distance from the tilt axis, and we can describe how the contrast varies using this tilt transfer function. And it's a function of this distance and the resolution theta and defocus. So it looks a little bit like a contrast transfer function, but it's got additional components in that you need to apply to correct and restore this central peak in the split spot. So if you want to understand this more, I would refer you to Richard's paper from 1990, which I listed at the beginning of the talk. So we do this TTF, or tilt transfer correction, in practice in Fourier space, but you still have to do all that unbending, which I hope you've already covered. So you correct the image, you correct all the distortions using the unbending techniques, which you hopefully are familiar with, but we have to do this additional tilt transfer correction. And there's a program called TT-Box. And what TT-Box is analogous to MM-Box, which I hope you've already encountered. And what that does is it outputs a set of amplitudes, phases, and so on, but corrected for this tilt transfer function. So you've got a list of amplitudes and phases for the Fourier components, but you're correcting for the tilt, defocus, and astigmatism. And here's a scheme of that's shown in Richard's paper from 1990. So this is what they settled on in that paper, this scheme of the steps in the processing. So in the initial stage, just concentrate on what's inside the orange box. You go through all the normal image processing steps, unbending and so on, as if the crystal was untilted. But instead of TT box to output the amplitudes and phases, use TT box, which corrects for the tilt. And you can use that then as a diagnostic of how well you're doing. So like with box, what you're looking for is maximizing the amount of power that you're getting into the diffraction spots in different resolution ranges, and you're looking for increasing your IQ values as you go through the processing. In practice, because the unbending and the TTF correction are not independent, you need to do cycles of refinement. So there are additional programs that allow you to do that. One of them is TT Refine, and basically that refines the defocus tilt angles, and then you can use those refined values to give you better values for either TT box or for another program called TT Mask. And TT Mask I'll come on to next. So in your straight unbending procedure on this side, you will have encountered a program called MaskTran, which masks your Fourier transform. So you're filtering it to allow you to start the unbending process. TT Mask is analogous, but it corrects for the effect of the tilt. So you're correcting for the defocus and the tilt using TT Mask. So it's like MaskTran, but it does a correction. And it produces sets of files which are analogous to those that you would use in the conventional unbending, but this time corrected for the tilt. And then you can go through cycles of unbending using these tilt-corrected data and cycles of refinement of defocus and astigmatism. In principle, TT Refine will allow you to refine the tilt geometry as well. In my experience, that can go awry, especially with highly tilted images. So its power is really in refining the defocus and the astigmatism. So you're going through cycles, and you're using TT box as a sort of diagnostic, like you would use box, looking how the diffraction amplitudes increase in power as you go through cycles, and looking for an increase in good IQ values for your spots. So those are the diagnostics of image improvement as you go through cycles of refinement of defocus and astigmatism, and cycles of unbending. But you've got to be very, very careful. Again, be really, really careful when you're doing this. Don't do it blindly, automatically, assuming that it's doing the right thing. So, particularly, for example, if you think of this tilt transfer function, if you don't get this right, you see how it's sinusoidally varying, it's repeating. If you don't get it right, you can end up getting stuck with the wrong defocus and astigmatism. So you've got to make sure that you're within roughly the correct defocus and astigmatism to start with. Let's say 1,000 angstroms. If you're too far out, you may end up locking yourself into a false minimum, which you won't get out of. So make sure that everything makes sense. The values you're getting in, let's say, TT Refine for your defocus and astigmatism, are they roughly what you expect just by looking at the tone rings in your image? Or are they wildly out? Be critical all the time. Make sure that everything fits and makes sense. So here's an example. Sorry, Richard, I had to scan this out of your paper because I couldn't find any of my own. But this is from Richard's paper from 1990, showing the unbending on purple membrane. And this is in the first step here. So here we've got the correlation peaks and the distortion vectors in one image. Maybe it's a 45-degree tilt image or something like that. And in the first stage, you treat it just like it was an untilted crystal. And by definition, normally, because you've taken the reference patch from the middle of the crystal, you get best correlation between the reference patch and itself in the middle of the image. And you can see you get a kind of narrowish band of good correlations. As you move further and further out, particularly into zones of low contrast because of the tilt, you get less contrast. So it's only really kind of working in a band in the middle of the image. So presumably the tilt axis is sort of somewhere along this direction. So either side, the tilt axis in a narrow band, you get good correlation, and it falls off as you get reversals in contrast or zero contrast. And this is after several steps of correction for defocus and astigmatism and allowing for the tilt angle. And now you find actually that the best parts of the crystal are actually all the way up here. So, and you get a much broader high correlation across the image as you go through cycles of unbending and defocus and astigmatism refinement. And this just shows the output for some spots at different resolutions, parallel and perpendicular to the tilt axis. And you can see at low resolution, that spot splitting manifests itself as a kind of stretching of the spots. As you go to higher resolution, you can actually see those little wings. So here's that central peak that's been corrected, but you can still see the wings that you would expect. And then at very high resolution, those wings are so far out that you don't see them. The other thing you've got to correct for is beam tilt misalignment. And this becomes important beyond about 6 angstroms resolution. So your illumination may not be perfectly perpendicular to your crystal, it might be slightly tilted. And it's analogous to coma, axial coma that you get in optics, where you've got a slight tilt of the illumination beam, and that causes a small change in the defocus and astigmatism and a resolution-dependent shift of the image components. So you get a shift of different components of the image depending on the resolution. And that shift can be split into 2 components. There's a simple shift of the whole image, which is easily taken care of, but then there's a resolution cube dependence as well, which you have to correct for. And you may end up having to correct for a slight tilt of the illumination of, let's say, 1 to 3 milliradians. And this becomes important, let's say, beyond about 5 or 6 angstroms resolution. So, for instance, at 3.5 angstroms, you might have to actually correct for a phase shift of somewhere between 200 or 400 degrees. So if you don't correct for beam tilt, your phases at high resolution will be meaningless. And this just shows how that phase shift is related to the resolution, so this diffraction angle, and the beam tilt. So again, I would refer you to some of the papers that I've described. And you can determine that beam tilt in just by looking at, you have to look at the phases, and there are 2 different ways. One, if you've got symmetry in your crystal, you can compare symmetry-related spots and see how well the phases agree. So you can try to correct internally for the beam tilt by trying to get those phases to agree as best as possible. If you already have a body of data, you can put in a new image and compare the phases against all the other body of data that you've already got. And you can do this in orange tilt. And because of that resolution cube dependence, basically you refine the phase origin on the low resolution spots and then refine the beam tilt on the high resolution spots. But again, don't do this blindly. These programs that are trying to optimize something, that are trying to give you a minimum or a maximum value, are always, by definition, going to find you a minimum or maximum value. It doesn't mean it's correct. So you'll always get an answer, but check that it's correct. So for example, If you've got a set of images from crystals that were all imaged in sequence, let's say, within one imaging session, and you haven't changed the conditions in the microscope, you'd expect the beam tilt to be the same in all those images. So is the magnitude and direction of the beam tilt the same in all those images that were taken in succession? If it's not, something's wrong. So make sure that it all makes sense. Do some internal checks. Here's an example from some of the data that we were working on. So here's a set of film numbers. All of these were from the same session, 509 to 527. And they've got roughly similar beam tilts, but 527 seems to be a little bit of an outlier. So I would go back to 527 and ask, is there something a little bit wrong? Check it. Here's an image from a different session, and that has a different beam tilt. When you've got tilted data, you have to do this kind of iteratively and carefully. Be really, really careful. So let's assume that you've got beam tilt corrected, untilted data. Then start to add your 20-degree tilt data and refine carefully the beam tilts by comparing against all the other data. So you compare one film against all the other data, and you do it slowly, carefully, going out to your higher and higher tilts. Okay, so I'm just going to finish off with some kind of final thoughts and observations. So you'll be looking at this in more detail, but just some thoughts about looking at maps, which these are just things that I've kind of over the years, just talking to people, new people that have come into the lab, trying to show them how to do image processing and look at structures. You're always going to have poorer data in that vertical direction. So you're going to get blurring in the vertical direction. Think about what you're going to expect at different resolutions. So at 20 angstroms, a small protein like this will just be a blob. And as you go out in resolution, you get more blobs. When you get to 10 to 7 angstroms, that's when you can start to expect to see alpha helices, for example. Be very careful if you have 4 to 5 angstrom resolution data. It can be very difficult to interpret. You can be very tempted to over-interpret your data and start trying to fit what you think are side chains, for example. You'll almost certainly get it wrong at this sort of resolution range, unless you know an awful lot about the biochemistry and the genetics. And for example, even well-determined X-ray maps at 2.5 angstroms resolution have been traced backwards. So be ultra, ultra careful. Get many data as you can. Don't overestimate your resolution. Just because you see a spot at 4 angstroms resolution doesn't mean you have 4 angstroms resolution. None of the programs that you're using are bug-free. Be aware of that. There are bugs. Things don't always work as they should. Don't use the programs blindly. Look at the log files. Are there error messages? Sometimes you get subtle little error messages hidden in the output that you didn't notice. Look for those. Make sure that if you see an error message, make sure whether it's important or not. Obviously, you need to make sure all your crystals have the same thickness when you're working on 3D. And if you've got more than one unit cell in this third dimension, things get very, very difficult. So hopefully you're working on very thin, single-layered crystals. And finally, I'd like to emphasize again, don't use the software blindly thinking that if you press enter, everything will work. Be ultra, ultra critical and make sure everything is sensible and you get consistency. And for instance, are your defocus values close to what you thought they were when you first looked at the tone rings. Are the phases sensible? If you're getting phase errors of 80 degrees, that's nonsense. It's not real data. Make sure you've got sensible phase errors. And be very patient and very, very thorough. Don't rush it. Just keep checking and making sure that everything makes sense. And then if you're careful enough, you should end up with some good phases that you can calculate a good structure from. And that's where I'll end.
All right. Questions, anybody?